Okay, I will speak now today about my hobby. This is soft phonon spectroscopy. Okay. And practically the aim is to explain you on several examples where is coming from dielectric anomaly at ferroelectric phase transition in displacive ferroelectrics, order disorder ferroelectrics, or in improper ferroelectrics, also in multiferroics. And if I will have a time, I will also mention electromagnons in multiferroics. Mael will speak after me about vibration spectroscopy, which is practically the same topic. We will see how we will overlap, but he will speak mostly about Raman spectroscopy, and he will show you how is it comparable with infrared spectroscopy. It depends on symmetry, of course, of the materials. So, dielectric permittivity. What is it? Can you tell me it? What is dielectric permittivity? Somebody has an answer? It's material parameter which shows you how good it allows the creation of electric field or in materials. You know this formula, and mostly we use it, this permittivity, for measurements of capacity. Everybody knows such formula. But most of people say that we have dielectric constant, but permittivity is, for me, is not constant. It's a complicated function of frequencies and also strongly temperature dependent. Therefore, if you would like to understand, let's say, permittivity in the kilohertz region, you should measure the whole frequency range to understand where it's coming from this permittivity. Here is schematically shown dispersion of real part of permittivity in X-ray range. You have relative permittivity 1, but then you have electronic transitions which enhance the permittivity here. Square root of permittivity is index of refraction. Then you have lattice vibrations, polar vibrations contribute to permittivity. The contribution can be 10, but it can be also thousands. And then you can have in ferroelectric materials contribution from domain wall motions, or in non-homogeneous systems with non-homogeneous conductivity, you can have additional dispersion, so-called Maxwell-Wagner relaxation, which can give you finally permittivity in millions. And so this frequency dependence can be expressed with sum of harmonic oscillators, or if you have dielectric relaxation, then you have sum of Debye relaxations. Ferroelectrics. Everybody know what is it, and discovered more than 100 years ago by Josef Valášek. By the way, Josef Valášek was an American with Czech origin. And what is typical for ferroelectrics? There is always strong dielectric anomaly at critical temperature. And so you can have here increase of permittivity to many thousands. And where is it coming from? Yeah? You describe it with Curie-Weiss law, but there is another formula, so-called Lidan-Sachs-Terrell relation, comparing static permittivity, it means low frequency permittivity, with high frequency permittivity, longitudinal phonon frequency and transverse phonon frequency. Let's say if you have only one phonon, polar phonon, you have such dispersion versus frequency, so increase of permittivity, and then it goes to negative value, and then it comes to high frequency permittivity, let's say epsilon infinity. So transverse or optical phonon is here. It is the frequency where is the highest absorption in material from phonons, and then longitudinal phonon frequency is defined that by 0 of permittivity. So you can imagine that if we have such Curie-Weiss law and permittivity goes at Tc to infinity, theoretically to infinity, then we should have transverse phonon frequency going to 0. And this is a concept of soft phonon described by Cochrane in 1960, but actually it was published earlier by Anderson in 1959, and by Ginzburg even in 1948. So important is that from both formulas you can finally obtain that the phonon frequency square is linearly temperature dependent. So phonon softening is responsible for dielectric anomaly in the case of displacive ferroelectrics. Displacive means that you have, let's say, atom in some position and then it displaces in another position, like it was here shown in barium titanate, that you have displacement of titanium in oxygen cage. Here is a classical example of soft phonon in such quite complicated system. It is tris-circosin carcinogen chloride, and there is softening and hardening to Tc, around Tc. Frequently in infrared spectroscopy and also in Raman spectroscopy, we use units reciprocal centimeters, which is, let's say here, 32 reciprocal centimeters or wave numbers corresponds to 1 terahertz. So we are in sub-terahertz range. And this softening of phonon, which is shown here in dielectric loss, you have this peak in loss corresponds to phonon frequency. So if you have decrease of phonon frequency, it is softening, and this softening is responsible for increase of permittivity. So this is displacive ferroelectric. But there are also many materials which don't show any phonon softening, and still they are ferroelectric. For example, some organic ferroelectrics, like this, I cannot read it, even such complicated chemical formula. In the case of displacive ferroelectrics, you have again dielectric anomaly at Tc, seen very well at low frequencies, 200 hertz, let's say. But if you go to higher frequencies, then the peak value is decreasing. It's still present at same temperature, but its value is decreasing. And then finally, at higher frequencies, you can have even minimum at Tc. Quite unusual, yeah, that you have at ferrotic phase transition minimum at Tc. And this is due to dielectric relaxation describing, let's say, in this organic system, you have vibration of or hopping of a big part of molecules among more potential minima, and this is somewhere in kilohertz range, and this hopping is slower and slower if you are approaching phase transition. So if you measure at high frequency, finally you don't see contribution of such hopping to permittivity, and therefore you see minimum at Tc. But if you measure at lower frequencies, all relaxation contributes here. Here is epsilon double prime, imaginary part of permittivity, showing this softening, and here it is shown this softening of the relaxation. So order disorder has such strongly frequency-dependent peak of permittivity. In the case of pure displacive phase transition, the peak of permittivity is almost frequency independent. But the life is more complicated. And in many cases, there is some crossover between displacive and order disorder mechanism of the phase transition. So far away from the phase transition, it looks like displacive. There is some phonon softening, but then close to phase transition appears additional dielectric relaxation describing some hopping of atoms among more position. There is a long discussion about mechanism in barium titanate. We believe it is more displacive type, But anyway, there are some signatures as well for the order disorder. I will explain it why. So in barium titanate, you know, there are 3 structure phase transitions: cubic, tetragonal, orthorhombic, rhomboedral. Polarization, it has jumps. Permittivity has again peaks. Again, due to such phonon softening, looks like. But what was observed that actually here in barium titanate there are 2 optical phonons or 3 optical phonons, and they show negligible temperature dependence. The lowest frequency phonon slightly changes, but not too much. But below phonon is another excitation. We call it central mode, and this is responsible for the dielectric, most of part of dielectric anomaly in barium titanate. So there is such model for order disorder mechanism in barium titanate that in cubic phase, when you have titanium in centrum of oxygen cage, it can be described that you have hopping of titanium in among 8 positions. So the hopping is somewhere in terahertz range frequencies. So in X-ray you see just middle position, but actually there is such hopping which is responsible for central mode. And at tetragonal phase, you have displacement of titanium along z-axis, and in this case you can imagine it like you have hopping only among 4 positions. And again, you can see some central mode. So in this case, when you have structure phase transition to tetragonal phase, the soft phonon splits. Here is one component, and here is another one. It is along c-axis. This is in AB plane. There is huge splitting, which is also responsible for much lower permittivity in C direction. This is phonon active in C direction. So permittivity is much lower. Here it is much higher, the permittivity A and B plane. So in other phase transition, you have again displacement here in this direction. Then you can imagine that you have hopping among 2 positions. And finally, in rhomboidal phase, only displacement along 1, direction. Actually, how it looks in barium titanate in infrared spectra. Here is an example of infrared spectra at several temperatures. These 3 bands corresponds to 3 phonons. I show here what does it mean, this vibration. So the most important is so-called Slater mode. This is vibration of titanium against oxygen vacancy. So finally, when this phonon is frozen, you have displacement of titanium along c-axis. Second mode shows displacement of the whole oxygen cage against barium atoms, and the highest frequency phonon describes just the formation of oxygen cage. Each phonon contributes to permittivity, but the highest contribution is from Slater mode. And what is actually observed, that there is a phonon softening and the splitting in ferroelectric phase transitions, but this is the soft lowest frequency phonon, but additional central mode is here present. And it is another picture of the same. So here is some crossover between displacive and order disorder mechanism. You saw this similar slide already in my lecture on Monday about strontium titanate. Strontium titanate is not ferroelectric. It is so-called incipient ferroelectrics. It means it is on cooling. It looks like it goes to phase transition. If you plot reciprocal permittivity, the permittivity goes to 0, let's say or reciprocal permittivity goes to 0 around 35 Kelvin. Looks like that here should be phase transition, but due to quantum fluctuations, the long-range ferroelectric order does not appear. And finally, at low temperatures, there is saturation of permittivity. So where is coming from such huge change of permittivity? Note here at room temperature, it is around 300, and at low temperatures is 24,000. Again, it is from phonon, soft phonon. and mostly the lowest frequency phonon is moving in reflectivity. It looks like this. It's very difficult to determine its frequency at low temperatures because, of course, we have reflectivity close to 100%, and there is, of course, some noise. But if you combine it with infrared, with terahertz data, which we have here, we can explain such phonon softening, and there is such lowest frequency phonon, how is it moving in logarithmic scale. And this softening is finally responsible for huge increase of permittivity. There is such, maybe it's good to remember, some rule for dielectric strengths or for oscillator strengths of polar vibrations. If you take this oscillator strengths, let's have only one phonon, practically. If it is not coupled with other, so you can take only one phonon softening. So if you have this product should be temperature independent, should be constant. So you can imagine if you reduce the phonon frequency twice, you should increase contribution to static permittivity 4 times. In this case, the phonon softening is even 10 times, and therefore you have finally 100 times higher permittivity at low temperatures in strontium titanate. Theorists calculate the phonons in Brahim zone in cubic phase, and frequently they obtain negative frequencies at some Q vectors, let's say in gamma point and also in R point. What does it mean? It means that this cubic structure is not stable, and it has tendency to go to lower symmetry phase. So this expresses the soft phonon, because in infrared spectra we can see only phonon from gamma point of Brahim zone. The rest of phonon we cannot measure using infrared or Raman, and it should be used, let's say, inelastic neutron scattering or inelastic X-ray scattering. But look here, there is on R point, there is also, it's even deeper minimum, showing tendency to another instability. And this is the reason why here appears antiferrodistortive phase transition. It means this oxygen or this perovskite structure, finally you have a rotation of octaedra. One octaedra is moving left, second to right. And so finally the unit cell is twice larger, and therefore you have multiplication unit cell at low temperatures, and appears as antiferrodistortive phase transition around 105 Kelvin. So what happens here, besides this, that we have a ferrotic soft phonon in gamma point, it is even split at low temperatures due to tetragonality, but at 105 Kelvin activates 2 modes in Raman spectra, which are activated from Raman, from R point of Brahim zone. Because if you have multiplication of unit cell, this R point, you have folding of Brahim zone to gamma point. And therefore these phonons come to gamma point, and then you can activate them in Raman spectra. I think Mael will speak more about selection rules, so I will not go in many details. Still, strontium titan is still not ferroelectric below 100 Kelvin. Therefore, it's the Raman mode is not infrared active, and infrared active modes are not Raman active as well. In 2004, was shown that the strontium titanate can be ferroelectric close to room temperature. If you grow strontium titanate on different substrates, you can induce the strain. In this case, was deposited strontium titanate on dysprosium scandate, and it has a larger unit cell or lattice parameter. So therefore you have tensile strain, and this tensile strain finally here is shown theoretical phase diagram. If you have tensile strain, you can, and here you have dysprosium scandate, or strain from dysprosium scandate, then polarization should appear in the plane of the film. If you will have compressive strain, polarization should be out of plane. In the case of such LSAT substrate, you can have it. What happens with phonons here? We know if you measure permittivity in single crystal, you have increase of permittivity on cooling due to soft phonon in bulk. But in thin film, the peak of permittivity node here is logarithmic scale. Here is peak of permittivity around 270 Kelvin due to ferrotic phase transition, and also when you measure infrared spectra, one can see the phonon softening around this critical temperature. So there is a phonon softening, hardening, activation of central mode close to phase transition. Again, there is some crossover from displacive to order disorder phase transition mechanism, and then also activation of other phonons at low temperature due to antiferrodistortive phase transition. While the soft phonon shows completely different behavior in bulk. In bulk, you have high frequency at room temperature and softening to 10 reciprocal centimeter, which is responsible for this increase of permittivity. So this is nice, mostly displacive phase transition with small contribution of order disorder. In European titanate, it's a similar story. It has a completely same crystal structure like strontium titanate. Lattice parameter is also completely the same, 3.90 something. And it has also antiferrodistortive phase transition, very similar things. But what is different is European titanate is also antiferromagnet. So Greg Fenny calculated this system, and he predicted that if tensile strain will be applied in this European titanate, then using such substrate, then the antiferromagnetic structure should change to ferromagnetic one, and paraelectric structure should change to ferroelectric one. So in this case, one should induce multiferroic properties in material which is in bulk, non-ferroelectric, and just antiferromagnet. And it was difficult to prove ferroelectricity because there is a leakage current and so on, but we measured infrared spectra. They are quite complicated because the substrate, dysprosium scandate, has many phonons. But have a look on low frequency part. If you have a thin film, in this case 100 nanometer thin film, thick, we have difference here, and this is reflectivity from the soft phonon, and on cooling we can see finally hardening of the phonon from here to here. So finally what we observe that soft phonon is at room temperature very low, it softens and then again hardens. So here is a signature of ferrotic phase transition. When we calculated contribution of the phonon to permittivity, we obtained such dielectric anomaly. And also polarization was calculated. It's quite large. So using infrared spectroscopy, you can prove as well whether you have a ferroelectric phase transition. And our colleagues measured magnetic properties. So using MOG, magneto-optic Kerr effect, in antiferromagnetic phase, in let's say in bulk or in thin film on strontium titanate, there is no strain, there is no hysteresis loop. But in the case of strained European titanate on dysprosium scandate, you can see finally nice ferromagnetic hysteresis loop. So it is proved that this system becomes finally ferroelectric ferromagnet. But the problem is that this measurement is at 2 Kelvin. The magnetization here appears only at 4.3 Kelvin, so it's very low. The reason is that for such low temperature is that also antiferromagnetic phase in bulk European titanate is at 5.4 Kelvin. So there is difficult to imagine that the phase transition will be at very high temperature. But it was just a demonstration when one can really induce multiferroic properties in a system which is not multiferroic, just due to strain. Relaxor ferroelectrics. I think it was a hot topic 10, 20 years ago, but last few years, I think less students is studying this properties. But what is typical for relaxors? You have in permittivity, temperature dependence, you see a huge peak, and which is strongly frequency dependent. In the case of classical ferroelectrics, you have peak of permittivity, and in the displacive case, there is the position of the peak is all the time same at different frequencies. So, but in this case, we have shift of the peak with higher frequency. So it looks like that we have ferroelectric phase transition dependent on frequency, which is nonsense, of course. And in dielectric loss, we can see such dispersion. So where is it coming from? This is due to, there is practically, in this system, it's not macroscopic ferroelectric phase, no ferroelectric domains, but only some polar nanoregions appear, let's say around 600 Kelvin, and they grow up on cooling and also fluctuate in direction, and therefore you have a dielectric relaxation of such movement of polar clusters. And Tagantsev explained it correctly that practically you have finally at low temperatures very broad distribution of relaxation times or relaxation frequencies, and therefore you obtain such broad dielectric dispersion in permittivity and loss. We prove it in this picture. Here are real and imaginary part at high temperature. So at the higher temperatures you see single narrow peak in microwave range. It means that this polar cluster fluctuates with gigahertz frequencies. And on cooling, you see softening of such relaxation and broadening. And finally, below 200 Kelvin, there is flat dielectric loss. These data are below 230 Kelvin. So permittivity shows just straight line in logarithmic scale, and loss is practically frequency independent. This is very broad due to very broad distribution of relaxation times. So wide loss practically is here. So this explains the dielectric anomaly in relaxors. But the question is, do we have some soft phonon? It looks like that we have some distribution of relaxation frequencies of these polar clusters describing flipping of polar clusters, or just if you have polar cluster, you can have also breathing mode of such clusters. But many years ago was already shown that high temperature permittivity follows Curie-Weiss law in the temperature range much higher than the peak of permittivity. So it looks like that there should be, if you plot a reciprocal permittivity, it should be like ferroelectric phase transition at 400 Kelvin. And so this is again such plot, reciprocal permittivity showing should be like this, the 400 Kelvin anomaly. But from neutron scattering is known that there is the lowest frequency phonon, which shows much smaller anomaly, and here again hardening. Unfortunately, in this temperature range, the soft phonon cannot be measured due to waterfall effect, which is another story which I will not explain here exactly. But important is it looks like that we have as well some contribution of soft phonon to permittivity. And we tried to understand it. So we measured infrared spectra, quite complicated here, but from 10 Kelvin to 900 Kelvin. In the case of cubic structure, there should be only 3 polar phonons given by symmetry. But finally, you see more bumps, that means more polar phonons, due to the fact that in polar clusters, you have broken centrum symmetry, and also you have distortion of lattice. So we assume that we have, let's say, permittivity along polarization of polar clusters with 30% probability, and 66% probability is here that we have polarization perpendicular to polarization. And then we model this reflectivity with effective media approximation. And what we obtained is a dielectric response, real and imaginary part, along polarization. You can see, let's say, peak here, slightly softening on cooling. And in AB plane, the E mode symmetry shows dramatic softening on cooling to 400 Kelvin. So finally, what we obtained that this mode is highly overdamped. Yeah? So I plot here frequency of the phonon square divided by damping. And it looks like that it shows softening according to Cochrane law to 400 Kelvin, and again hardening. And it explains change of permittivity above TC. So in this case, we have ferrotic soft mode within polar nanoclusters, and then you have dynamics of polar clusters below 600 Kelvin, which also is responsible for broad dielectric anomaly and much higher permittivity at low temperatures. Now I have to stress that in this case the phonon contribution is just less than 1,000, or here in this direction only less than 300, while you saw it before temperature peak permittivity around 250 Kelvin is 20,000. So dielectric relaxation is much stronger. Well, so I try to explain origin of dielectric anomaly at displacive phase transition in the relaxed source. But there are also some ferroelectrics which show just strange anomaly. You can have just jump and very low permittivity. Also such jump, there are different compounds. This is gadolinium molybdate. It shows tiny peak at TC. The polarization is in such materials is very small. It's 1,000 times smaller than in barium titanate. So where is it coming from? It was explained already in 70s by Dvořák and Levaniuk, Sanikov in such 2 nice reviews. And they invented the term improper ferroelectricity. So you saw before in Marty Gregg lecture that you have free energy expansion to order parameter like this, Q squared, Q force. But imagine that you have also another order parameter. In this case, you can have a quadratic coupling of order parameter, which is not polarization in this case, but it is coupled with polarization. And then this coupling is inducing polarization. Due to this coupling, the polarization is weak. It also is responsible for small dielectric anomaly, but it can exist. And I will show you on the next slide example. But there is also so-called pseudo-proper ferrotic phase transition when you have just bilinear coupling of order parameter and polarization. So in the case of improper ferroelectrics, you can have coupling. The order parameter can be, let's say, strain. You have first ferroelastic phase transition, and it can induce also polarization. In the case of pseudoproper, you can imagine that all the parameter is, let's say, magnetization in multiferroics, let's say, and it induces tiny dielectric anomaly of this shape, like in terbium manganite. Here is example of improper ferroelectric phase transition in hexagonal barium manganite. Most of hexagonal manganites have phase transition above 1000 Kelvin. In this case, the phase transition is just around 130 Kelvin. And what we observe in permittivity, temperature dependence, and at different frequencies. Have a look on high frequency at around almost 1 megahertz. So we have temperature independent permittivity, and then change of slope, increase of permittivity, and then you have dispersion here. So here it looks like a relaxor ferroelectric. But when we measure polarization, we found that the ferroelectric polarization is already at this temperature. And there was also theory showing that from high temperature phase, which is or pyroelectric of this symmetry or paraelectric of this symmetry, with 2 unit cells, that it should go to with larger unit cell with 6 formula units, and so this finally this hexagonal phase has such symmetry. So this is due to improper ferroelectric phase transition. I will show you another evidence. You can ask, what is this frequency dependence here? You can see frequently strong frequency dependence of permittivity and even giant permittivity at low frequencies if the system has small conductivity. Then you have inhomogeneous conductivity in the system. You can have, let's say, close to electrodes depletion layer, which gives you a huge capacity because the depletion layer is very thin, and the rest of the bulk does not contribute to permittivity. So you can measure huge capacity, and it looks like that you have giant permittivity, but it is just so-called Maxwell-Magnet relaxation mechanism for appearance of relaxation. But here, what is here, it's not a relaxor ferroelectric, but if you can imagine that if you have ferroelectric phase, the domains have a vibration due to temperature, and these domains freeze out on cooling, and this freezing is strongly frequency dependent. Therefore, you have such decrease of permittivity. What is another evidence for this phase transition is phonon spectra. So what happens here, that in paraelectric phase, the phonon branch in the whole Brahim zone is softening only at Brahim zone boundary. So we cannot see such phonon in infrared spectra because Q vector of infrared radiation is almost 0. So we can measure only phonons in gamma point. So the phonon softening is here, and then at low temperatures, you have multiplication with itself, and you have folding of Brahim zone to centrum, and this phonon comes to Brahim zone center, and therefore it can be activated in infrared spectra, which is shown here. I have here spectra from our time domain Terra spectrometer, showing better look in dielectric loss. You have some weak peak close to phase transition, but the peak becomes stronger and stronger, and it's shifting to higher frequencies. The frequency is here shown versus temperature. So we have hardening of the phonon. Permittivity shows also nice anomaly. So this is evidence that we have really soft phonon above phase transition, and below phase transition, this phonon hardens on cooling due to this multiplication with itself. And we prove this phase transition as well, not only from X-ray, but also from electron microscopy. The dispersion, diffraction in electron diffraction shows some satellites corresponding to multiplication of unit cell. Okay, multiferroics. You had already a nice talk about multiferroics, so I can go faster here. We are mostly interested in magnetoelectric multiferroics, where you can influence polarization with magnetic field or magnetization with electric field. So in ferroelectrics, you have such a Landau expansion, but in the case of magnetoelectric multiferroics, there is not only electric field square and magnetic field square, but there is also a linear coupling between magnetic field and electric field. So here is linear magnetoelectric coefficient, or you can have higher order magnetoelectric coupling. Important is that in multiferroics, we need strong linear magnetoelectric coupling, and this linear coupling is allowed only in the case when you have no special inversion symmetry, which is in ferroelectric phase, and no time reversal symmetry, which is in ferromagnets, and but also in some cases of antiferromagnets. In the case of chromium oxide, which was first a linear magnetoelectric system, you can see the induction of polarization with magnetic field, which is linearly changing with magnetic field. So this is evidence for also one of the evidences for linear magnetoelectric coupling. In the case of bismuth ferrite, everybody heard here already many times, the polarization is increasing with magnetic field quadratically. So there is a quadratic magnetoelectric coupling. There is no linear magnetoelectric coupling. And this is due to the fact that you have cycloidal spin structure and the time reversal symmetry is not broken. You need good collinear magnetic structure, antiferromagnetic structure, and then you can have linear magnetoelectric coupling, which appears here above 20 Tesla. If you apply magnetic field 20 Tesla, then okay, you switch the polarization, but doesn't matter. But then you can have strong magnetoelectric linear magnetoelectric coupling. You already heard about type 1 multiferroics, where you have independent ferrotic phase transition and independent magnetic phase transitions, which can be due to mixed perovskites, or ferroelectricity due to lone pair, like in bismuth ferrite, charge ordering, or geometrical ferroelectricity. Typical example is yttrium manganite. In the case of type 2 multiferroics, you have first magnetic phase transition, and then due to spin coupling, for example, if you have non-parallel spins, you can have this inverse Jaushinski-Moria interaction, which is responsible for creation of polarization. In the case of collinear magnetic structure, there is a just exchange friction, which produces polarization. In this case, the polarization can be much higher than in this case. The first discoverer of this, or it is practically second material, but most popular material is terbium manganite, when Kimura published in Nature such dielectric anomaly. So there is small change of permittivity. So first there is magnetic phase transition around 40 Kelvin, then decrease of permittivity, and then sharp peak, but very narrow and very small. And then when he applied magnetic field, he observed, okay, below magnetic field there is a polarization along C-axis, and when he applied magnetic field along B-axis, the polarization decreases and appears in A direction. So what happens here, that you practically rotate with spins, and therefore you finally induce polarization from you rotate polarization from C direction to A direction. And this was explained by Jaushinski-Moria interaction. You have non-parallel spins here. where is coming from such tiny dielectric anomaly? Yeah. Kimura has such tiny anomaly, and he does not mention even frequency when it was measured, probably around 1 kilohertz or 10 kilohertz. When my colleague measured permittivity in this system, in broader temperature range, you can see giant permittivity at high temperatures due to Maxwell-Wagner relaxation. And then at TC, there is this tiny peak. And it is shown in broader temperature range or narrower temperature range here, but better just around phase transition. What happens? Frequency dependence. The low frequency permittivity, 10 hertz permittivity, shows quite large anomaly, but it's very narrow. Yeah? Have a look, it is less than half Kelvin. And then this position remains at all frequencies, but intensity of this peak decreases, value decreases. So this is typical signature of improper phase transition. So we have here this magnetic order which inducing ferroelectricity, and you have strong dispersion, but very narrow, very small dielectric anomaly at TC. So I mentioned the Jaloshinsky-Moria interaction, which can induce polarization in cycloidal systems or transverse conical structures, exchange friction, and there is a third mechanism, spin-dependent hybridization of electrons. And but what was also interesting that in terbium manganite, same compound, when the Pimenov and Takahashi measured infrared and terahertz spectra, they found some phonons at high frequencies, but at low temperatures, some additional absorption appears. Even two peaks are here, and these peaks were explained like electromagnons, electrically active magnons. So what happens here? It is electrically active excitation because this phonon strength decreases on cooling, and the strength is transferred to these two excitations. So this is evidence for electrically active excitation. There is even crystal field excitation as well. And why they claim as well that it is electromagnon? The point is, or electrically active, for determination you have to measure terahertz spectra at all possible polarizations. You have to imagine that terahertz radiation has electric vector and magnetic vector and some propagation vector. And when they measured spectra with electric vector along A-axis, they see two excitations very similar for two different magnetic vectors along B-axis and along C-axis. But in the case, if it would be just magnetic excitation given by magnetic vector along B-axis, then it should be seen in this spectra, but it is not seen. So it is seen really due to this electric polarization of terahertz radiation. So therefore it is electrically active magnon. And you can imagine it like that it is vibration of spins like this. There are two electromagnons, so you have fluctuation of polarization along C-axis, and it is interesting that this polarization of electromagnon is along C-axis, but it remains also in high magnetic field. I shown before that the static polarization can be rotated from C-axis to A-axis. Due to Jaloshinsky-Moria interaction, you change the spin orientation and polarization. But in this case, electromagnons is independent on magnetic field. So the origin of electromagnon is not Jaloshinsky-Moria interaction, but exchange friction. And it means different mechanism for magnet. It is so-called it is induced by dynamic magnetotic coupling, and this dynamic magnetotic coupling can have different origin than the static magnetotic coupling. So actually here, these two electromagnons from exchange friction are activated at Brouwen zone boundary and in some special point of Brouwen zone. And there can be also Jaushinski-Moria electromagnon, which is very weak in another spectra, but mostly are seen these two excitations. Another typical feature, which was explained better by Nagaosa here, is for electromagnon is that there is a directional dichroism. So imagine that you have propagation of terahertz radiation in one direction, let's say here, and if you have polarization up and magnetization to you, and if you will have a propagation in opposite direction, the absorption will be different. So you can imagine like that you just switch to magnetization here. You have polarization all the time the same and magnetization in opposite direction. And then finally, the absorption will be different, which is quite surprising. Normally, it does not matter if you measure transmission along one direction or opposite direction. The absorption is the same. But here, due to magnetoelectric coupling and due to off-diagonal magnetoelectric susceptibility, the magnetoelectric coupling or this absorption is dependent on direction of propagation of terahertz radiation. This was observed as well in bismuth ferrite. In different magnetic fields, you can see different absorption in two different directions, blue and red. So you can even imagine that if you will optimize the magnetoelectric coupling, that you will have transmission in one direction 0, you have total absorption, and in in opposite direction you will have good transmission. So you can make some invisible code dress. Yeah. The magnons are in bismuth ferrite changing quickly, dramatically with magnetic field, but I don't go in details. The electromagnons actually in bismuth ferrite are activated out of Brouwen zone center due to cycloidal magnetic structure. So you have incommensurate modulation of structure, and you can activate the magnons at Q vectors of the modulation. And the modulation in bismuth ferrite is 62 nanometers, so Q vector is of this modulation is quite small. And due to this electric activity of electromagnon in Raman spectra, it can be also seen in Raman spectra, the electromagnon, not only in terahertz spectra. The electromagnon is also dependent on electric field. So you can imagine that you can control electromagnons using external electric field, which could be helpful for magnonics. Let's say that you will not need the magnetic field, but you will need just electric field. In this paper, you can find all different structures, magnetic structure, where this electromagnons or non-reciprocal light propagation can be observed. Yeah, here is literature compounds, and so if you are interested, you can have a look in this paper. The electromagnon can be also not in microwave range. So for magnonics is again interesting. So in this paper was shown that in hexaferrite of this kind, this propagation of the electromagnon depends on direction of magnetic field or of magnetization. So there is really direction dichroism of electromagnon also in microwave range. I think I will not go in many. I had here another example of electromagnon in hexaferrites, but I don't have too much time. In hexaferrite, it's very funny. It's ferrimagnet, and you can have different magnetic structures. It depends on composition and temperature. And in Y-type hexaferrite with 22 oxygens, the magnetoelectric coupling has a different origin than in Z-type hexaferrite when you have this symmetric change. This is due to this spin-dependent metal-ligand hybridization, while here this is the magnetoelectric coupling due to Jaushinsky-Moria interaction. So note, the chemical composition is somehow very similar, but finally it has a different magnetoelectric coupling. And I would like to stress that in this case, the magnetoelectric coupling is seen also above room temperature. So it's room temperature multiferroic up to 400 Kelvin due to this transverse conical magnetic structure. And there is also electromagnon seen in C spectra of terahertz radiation around 1.5 terahertz, while in electric vector of terahertz radiation along A direction, it's not seen. And it is very strong as well in Raman scattering. But important is that this electromagnon disappears in magnetic field above 3 Tesla or 2 Tesla because this transverse conical structure changes to collinear structure. So, you change the magnetic structure and you kill activation of electromagnon. But here, ferromagnetic resonance comes from microwave present without magnetic field to 300 gigahertz with magnetic field, let's say 7 Tesla. The electromagnon has origin in exchange friction in this alternative longitudinal conical structure or transverse conical structure. Yeah, I have 10 o'clock, so I should stop here. I wanted to demonstrate here that the observation of soft phonons in soft modes in microwave, terahertz, infrared range, and also possible in Raman scattering, which will be shown in next talk, is essential for understanding of dynamics of ferrotic phase transitions. And you can also study such optical soft phonons in strained thin films, like strontium titanate and europium titanate. The magnetoelectric coupling, dynamic magnetoelectric coupling activating electromagnons can be different, not necessary, but in some cases it can be different than the static magnetoelectric coupling responsible for static polarization. So you can see it in hexaferrites that you have, in this case, completely different change of polarization versus magnetic field. Thank you for your attention.